Hello and welcome. Today we will see a derivation related to the strain energy due to axial force or axial load. For that, I am considering a member of constant cross-sectional area subjected to the axial force throughout the centroid of the cross-section as shown in the figure. Also, I am considering a small element of length dx under the action of axial load P applied at one end. Gradually the beam gets elongated by U and the small elements get elongated by du. Okay, that's what I consider. See here that I can explain you. Just I am considering a bar which is fixed at one end and I am applying a load of magnitude P It is a tension load. So what will happen due to this load, and this bar is having a length of capital L and its cross sectional area I am considering it as capital A. Okay, and due to this load this bar will be extended by an amount of U. Okay, due to the application of load P, the bar will get extended by the amount of P. In addition to that, I am considering a small element in the total bar, that small element having the length of dx. Okay, that's what I considered, small element having the length of dx, and that dx will undergo deformation. That I am considering it as small deformation. That one I am considering it as du. Okay, that you have to keep it in mind. So that you can see here, just I am considering a small bar, okay, which is fixed at one end, and I am applying a load. Okay, okay, pulling load. So due to this bar will elongated. Okay, that elongation amount I am considering it as U, and a small portion in the bar I am considering this portion having a length of dx. This small portion will be elongated due to this load P. That will be, I am considering it as du, that is small element deformation du. Okay, from this I can consider, we know the formula, that what I given here, that you can go through once again, that I explained earlier. Okay, stress that will be equal to load by area. Here load is P and cross sectional area is A. Okay, and we know strain of a element, not the total bar, element. Okay, only element. So element having the length as dx and it will undergo elongation as du. That you have to keep it in mind. Dx is the length of the element, du is the elongation of the element. Okay, then strain will be given by change in length divided by original length. So change in length is du and original length is dx. Okay, and we know by using Hooke's law stress will be directly proportional to strain. Then we can say that is stress will be equal to product of E into strain. Okay, where E is the Young's modulus. Okay, from this equation I can easily consider strain will be equal to stress by E. Okay, that is Young's stress by Young's modulus. Okay, that's what I considered. So just I am cross multiplying this equation. That is du will be equal to dx into strain. Okay, epsilon. Du will be equal to dx into epsilon. That's what I considered. And we know strain will be equal to stress by Young's modulus. Okay, that I substituted here. Okay, then what will happen, just for the further simplification, we know stress will be equal to load by area. So that I consider in place of stress I am considering load by area. Okay, in place of sigma I am considering load by area. Then it will be equation you will get as du will be equal to P into P divided by AE into dx. This is for the small element of length dx and undergo deformation of small deformation du. So in order to get the total length of the bar, then what we have to do, we have to integrate the above equation with respect to 0 to L. Okay, that's what I considered here. So for total length of the bar, I am integrating above equation, then integration of du will become u. So that's what I considered here. And we know from the principle of virtual work, that is work done by external load will be equal to, even we can consider directly, that will be equal to strain energy. Okay, so work done, I am considering it as half into load is P for the total bar, and it will undergo deformation as U. Clear? Is it clear? Yeah. So from that, now I can say work done will be equal to internal strain energy stored. Okay, external work done will be equal to internal strain energy stored from the law of conservation of energy. Then I can equate strain energy will be equal to this. Okay, that's what I considered. So strain energy will be equal to total work, that will be equal to half into P into U. In place of U, you know the value of this U, that is a total length deformation, that I substituted here. Then I am integrated that equation with respect to L to get the total beam. Okay, in order to get the total beam, so I am integrated that one with respect to L, then I get the equation as this. Okay, this is the total strain energy when a bar is subjected to axial load along the centroidal axis. Okay, centroidal axis. Yeah, this one is a very important one that you have to keep it in mind. Okay, thank you. We will see some more derivation in upcoming videos. Thank you.